Okay. Well, thanks, Eric. Yeah, I'm looking forward to our talk tonight. In last week's session, How to Lie with Maps, I confess that I love maps. And based on the feedback that I received after that talk, I'm not alone in that feeling. I think people are seeing maps with new eyes now after the things we talked about there. And I know tonight we have a lot of passionate map lovers with us again tonight. So I have good news. This talk is also about maps. It's about how to locate ourselves on maps. And again, tonight, I want to start with something I think on which we can all agree. Maps can be incredibly useful. And in many cases, just how useful a map is depends in part on what seems like a really simple question, and that is, where are you? You are here. Last week, we talked about a world where we could have a map with south up and how that caused us to see the world with new eyes. And we talked about how that's completely valid since the Earth is floating in infinite space and north up on a map is just a convention that we've adopted, but there's really no up or down to space. And that point is well illustrated, I think, by this You Are Here map. We talked about the pros and cons of Google Maps last week and how some of the 2 billion users of Google Maps each month find themselves in this unfortunate situation. You were here, now you're lost. And we also looked at Google Map fails like these, where Denver airport drivers got stuck in the mud using Google Maps, and a Texas case where a woman's home was accidentally demolished due to a Google Maps error. And we saw how folks try to solve these high-tech problems with low-tech solutions, signs that say, Google Maps is wrong, you're fooled by Google Maps. And often in the media, these kind of problems are portrayed as a GPS problem. Like this example from Yorktown, Virginia, where the headline equates a mislocated business with GPS. Yorktown Pub, Grafton residents at odds with GPS. Or in Death Valley, where our national park posts this warning, quote, GPS navigation in remote locations like Death Valley are notoriously unreliable. Numerous travelers have been directed to the wrong location or even dead end or closed roads. So GPS even gets a bad rap in Wikipedia, where there's an entry called Death by GPS that refers to folks who've died after following GPS directions or GPS maps. So it makes sense then, logically, a lot of folks who think this is a GPS problem and they go to the organization that runs GPS for an answer, and that's the US federal government. Well, the federal government site for GPS is gps.gov. And when you go to that site to complain about getting stuck in the mud or your house being accidentally demolished, here's what you're going to find. Frustrated by missing or wrong locations? The problem is in the mapping software used by the devices. The software comes from the private sector, Google, Apple, etc., not from the GPS satellites. GPS satellites are simply beacons, like lighthouses. The satellites do not transmit any mapping information. And then in bold from our US government, the government cannot correct any mapping errors in consumer devices. But they offer some links, and when you click through how to report a mapping problem affecting GPS devices, you end up at a screen that is the same screen we visited last week for Google Maps, as well as links to other mapping softwares and mapping companies that provide the option for users to report problems. So step one is you click one of these links and you report a problem. And then step two is my favorite. Step two says, wait patiently. Any fix is going to take a while. But in this text also, I think, is a key difference between two types of GPS systems. People who use their phones are going to get updates as soon as the mapping company makes those updates. But dedicated GPS devices like those that are typically found in cars are going to need a manual update. And to quote the GPS Gov site, unfortunately, most people do not update their devices regularly. Well, that's true. And then step 3, GPS only gives you the blue dot. It doesn't provide the map. Please contact the companies that produce them. Well, one of those companies is Garmin. And Garmin is one of the biggest players in this market. Garmin was founded in 1989 in the Kansas City area and is still headquartered in Metro Kansas City over in Olathe. They were one of the first to market with this technology, and they really rode the wave of GPS popularity. And their products are fabulous. They have over 13,000 employees now, over $3 billion in annual revenue. And we'll talk in a few minutes about some of the changes in the GPS industry that led to this incredible growth. But here right at the start, I want to make sure we clarify what we're talking about, some of our acronyms. We all know the acronym GPS, and we use it to mean Global Positioning System. But like most things in life, when we go a little deeper, things are a little more complex. In 2020, we live in a world that has 4 completely independent, unique global navigation satellite systems. The US system, a Russian system, a European Union system, and a Chinese system. GPS is the name of the US system. The much less familiar acronym is GNSS, which stands for Global Navigation Satellite Systems. And that's the acronym we use when we're referring to all 4 of the systems. But just like folks call all tissues Kleenex or all blue jeans Levi's, you're going to hear me tonight say GPS when I probably should say GNSS. And I'm going to leave it up to you to translate and understand what I'm saying. So I want to take a few minutes and understand these systems using a really tried and true method that every journalist is taught in school, and that is to answer the questions who, what, when, where, why, and how. And we're going to have some fun along the way with GPS. We're including Chiefs coach Andy Reid, who was recently GPSed into a farmer's field. And for fans of the British monarchy, we're going to take a trip to Victoria, British Columbia to see Queen Victoria GPSed onto that city's street grid. But I want to start with the who, what, when, where, why, and how, with who are the big players in the GPS world. And I'm going to start with the US system. We all know it, the GPS system. The first satellite in this system was launched in 1978. And 15 years later, in 1993, the 24th satellite was launched. And that offered, for the first time, worldwide coverage in this system. It's been in continuous operation for 27 years, but for the first 7 years, the system was limited on the public side to about 100-meter accuracy. The military side had much better accuracy, but in the year 2000, President Clinton signed an order that ended this intentional scrambling, or what was called selective availability, on the public side of the system, and GPS got a lot better. So Garmin at that point was really well positioned, having worked with the military side, to take advantage of the consumer side, the public side, when selective availability was turned off in 2000. Now, over the years, there have been a number of satellites launched to replace outdated satellites or damaged or inoperable satellites. And so what we have in this system and every system we're going to talk about is a mix of old satellites, middle-aged satellites, and brand new satellites. And each of these have varying capabilities, but they all work together to generate the kind of location data we expect. Now, in the case of the US system, just in the first week of November this year, a new satellite was launched. It came online the first week of December, and we'll talk more later in the how section about the specifics of how these satellites all work in unison. The second system I want to cover is the Russian system. It's called GLONASS. Their first satellite launched 4 years after the US system's first satellite. Their system was operational with 24 satellites, and we'll talk later about why 24 is a magic number. But in 1995, they achieved worldwide coverage. But shortly after that, their satellite system fell into disrepair because of a lack of funding, the breakup of the Soviet Union. And for many years, they focused their satellites only on the area around Russia and did not have worldwide coverage. But in 2011, they had upgraded their system, launched more satellites, and again, restored worldwide coverage. The third system is developed and operated by the European Union. It's called Galileo. Their first satellite launched in 2011, and they achieved worldwide coverage in 2019, which was 26 years after the United States system went into operation. Both the Galileo system and the Russian system offer stronger coverage in extreme northern latitudes as compared to the US system because of the geography of the planet and where most of their interested users are located. And another difference is the Galileo system was developed not intended for military use as its primary use. The other three systems were all developed with the military in mind. And then the fourth system from China is called BeiDou. And China was involved in the development of the European Union's Galileo system at the start until about 2006. China has had several versions of BeiDou. System 1 and 2 offered regional coverages in the Asia area around China. And then BeiDou 3, which is the current system, achieved worldwide coverage a couple of years ago in 2018. There are a couple of regional satellite-based navigation systems that I'll mention briefly. One is the Indian system. It has 8 satellites, and it covers the areas that I show here on the map. It was developed by the government of India to be a regional system. It's completely independent from the other systems. All of the componentry, the satellites, the receivers, everything were developed, designed, and manufactured in India. And their system works very well. It's very concentrated on that part of the world. The other regional system actually works in concert with the US system. It's the Japanese system. It has 4 satellites, and the orbits of those satellites are tailored so that they spend almost all of their time right over Japan. And that gives some advantage. We're going to talk in a few minutes about some of the problems that with GPS when you're dealing with areas with tall buildings that are close together. And the Japanese system sort of helps to overcome some of the issues that are inherent in satellite systems because of the location of these special 4 satellites. So that sort of covers the who and the when, I think, of the major systems. And I want to talk now about the what. What are the components of the systems? Well, all of these systems have 3 components. A control segment, which involves people in bunkers, in secret locations that are making sure everything's working together. There's a space segment, which are the satellites that are flying thousands of miles above the Earth. And then there's the user segment, which is those of us carrying around GPS devices, whether they be in our car, our phone, etc. And I think it's been too long since we've seen a map here in this talk. So here's a map of the control segment for the US system. And the GPS master control is at Schriever Air Force Base in Colorado. It's one of the few Air Force bases that does not have a landing strip. All these ground control stations monitor and relay information up to the satellites and back to the central master control in Colorado. Each one of those 4 systems that I talked about have their own equivalent of this system that are completely independent of the US system. And here's a little more detail of how this ground control system functions. There's a 2-way communication between the satellite and ground control. they can send information to the satellite about its orbit, about its positioning, and about its clocks and all the things that are there. But you see on the receiver side, we only receive data from the satellite. Your GPS receiver doesn't send any information back. It's a completely one-way communication on that side. We move on now to the space segment. This overly complicated chart kind of shows how the system works in terms of orbits. There are 6 orbital planes in the US system that are listed across the bottom of the screen, A through F. And those different orbital planes have at least 4 satellites that are spaced into slots along each of the planes. So 6 planes, 4 satellites, that's the 24, 6 planes. So the 24 satellites are needed to achieve worldwide coverage. Each of these satellites circles the Earth twice a day. And on the right here, there's a little chart that sort of indicates the different ages of these satellites that are color-coded. Some of the older ones and then some of the newer ones as well. So you can see there's sort of a mixture of satellites in the system. If we take that chart and turn it into more of a 3D kind of graphic, you can see that these satellites are spaced such that from any point on Earth, you should be able to see a minimum of 4 satellites. And we'll talk about why that's important. It's critically important. If we animate this image, you can see that this assumes that you're stationary on the Earth. And as the Earth rotates and as the satellites rotate through their orbits, the number of satellites that are visible from your spot on Earth is constantly changing. Knowing that we need a minimum of 4 satellites, and the more satellites, the better to a certain point, you can see that GPS is not the same morning, noon, and night. The satellites are constantly moving along with the Earth. Well, if you want to see a GPS satellite without going 12,000 miles into space, the San Diego Air and Space Museum has what they say is the only one that's on display in the world. This was an early model that was built by Boeing, and it was used for thermal testing but never launched. If you want to get a sense of the size of these space vehicles, these are photographs from Boeing for a more recent one of the GPS-2F satellites as it was being built in Boeing's facility. So you can get a sense there of scale compared to the folks working on it. So let's talk now about the where. If we look at this image of orbits around the Earth, you can see the GPS satellites are sort of clustered here on this chart. They're roughly 12,000 miles from Earth, but the satellite orbits range between 12 and 17,000 miles. Each of the 4 systems has their own orbit that they use, so there's no interference in terms of orbit. And to answer the question, where are these services available? The answer is almost anywhere there you have an unobstructed view of the sky. New and more sensitive receivers have increased the likelihood that you're going to get a valid GPS signal in places that formerly had spotty service, for instance, under tree canopy or in urban canyons, under bridges, in your car, indoors, other areas where part of the sky may be obscured. But to answer this where question, we also, I think, have to talk about the idea of jamming GPS. And on the GPS Gov site, it makes it very clear that jamming GPS is against federal law. And further into the site, there's a list of actions that the federal government has taken against folks selling and promoting the use of these jamming devices. But if you just jump out on eBay right now, for 20 bucks, you can buy a device that claims to be a GPS signal blocker that plugs into the cigarette lighter of your car. Whether it works or not, I do not know. But I think the most high-profile case of GPS jamming involved a CIA drone that was involved in a case of GPS blocking and spoofing. This was in 2011. Iran claimed to have spoofed the GPS such that it caused this drone to land safely at an Iranian airfield instead of at its home base in Afghanistan. Now, this is a CIA product, this particular drone. And so the US officials confirmed that this was a US drone that was captured by Iran, but they disputed the idea that it was done by spoofing GPS. They stated, quote, GPS is not the primary navigation sensor for this particular drone product. I think that military story kind of leads nicely into our answer to the why question. Why was GPS developed? The answer is to answer the military question, where am I? Other countries developed their systems in part so they were not reliant on the US system. But in addition to their where am I responsibilities, the GPS satellites have a couple of other interesting functions. Each satellite carries a nuclear detonation detector, and that would alert the United States to that kind of activity anywhere on Earth at any time of day or night. Another thing that the GPS satellites do is they keep incredibly accurate time, down to less than a 40 billionth of a second in terms of accuracy. And many land-based systems have come to rely on GPS for coordinated timing. Now for the how. I think this is the fun part. How can a device that we have in our pocket communicate with satellites 12,000 miles away? Well, I'm going to start with an example. Let's say you're completely lost, but you have two pieces of information. One is that you are on the surface of the Earth, and the second piece of information is that you're 800 miles from Dallas, Texas. So you know from those two things that you're somewhere on this circle. Well, if you get one more piece of information that says you're 400 miles from Kansas City, now that's progress, because we know we're either in South Dakota or in Indiana. And if you get the third piece of information that you are in fact 600 miles from Atlanta, then that puts you in Indianapolis. And I've heard this approach to locating being compared to the kids' game Marco Polo that they play at the swimming pool. Well, that's kind of how this works, although in the real world, we're talking about 3 dimensions. And let's expand this example to do just that, take on a 3-dimensional world. So if we have a satellite and we're talking about all points equidistant from that satellite, that creates a sphere. If we have a second satellite, its sphere intersects, which creates a circle. The third satellite intersects the first two and gives us 2 points on that circle. And then the fourth satellite completes the puzzle and locates us. So the answer to the quiz question, how many satellites are required to achieve a GPS fix, is 4 satellites. What could possibly go wrong with a system like this? There are so many factors that impact GPS accuracy. I want to visit a few of those. And the first one is the Earth's atmosphere. All GPS satellites orbit above the primary layers of the atmosphere, and the signals must pass through the atmosphere in order to make it to our receivers on the ground. It's the ionosphere that really creates havoc with GPS signals. The only question really is how much havoc. There's a lot of solar activity, ultraviolet rays and X-rays that really bombard the ionosphere and keep it in turmoil all the time. It's really constantly changing hubbub out there. Well, why is that important? Well, we use the time that it takes for that signal to go from the satellite to the receiver as a way of calculating a distance value. And here's what I mean. These examples of speed of light, you see Earth to moon there is only 1.3 seconds. Well, the GPS satellites are much closer to the Earth than is the moon. In fact, those signals take just over a half a second to arrive at the surface of the Earth. And given the scale of the numbers involved, if our time calculation for that signal is only off by 1,000th of a second, then the distance measurement would be off by over 150 miles. And would you use a GPS that said turn right somewhere in the next 150 miles? I don't think so. Another component of this involves relativity. The satellites are moving at a high rate of speed relative to the Earth's surface, and they are 12,000 miles away from this large mass of the Earth. And both of those issues or those relationships can create issues with clock accuracy, and they have to be accounted for using general and special relativity calculations. So if we didn't apply what Einstein discovered about relativity, the differences in the clock speed would introduce errors of at least 10 kilometers every single day. So thank you, Albert Einstein. And thank you, Gladys West. Dr. West worked for 42 years for the federal government in research, mathematical modeling, and satellite geodesy, which ended up serving as a foundation for GPS. She was inducted into the US Air Force Hall of Fame. In a recent interview with The Guardian, she said that she prefers using paper maps over any kind of a satellite-based tracking system. She says, if I can see the road and see where it turns and see where it went, I'm just more sure of things. So thank you, Dr. Gladys West. Her research on satellite positioning and how they relate to the Earth is a huge part of GPS. For example, if the visible satellites at any moment are kind of grouped close together high in the sky, that's not as good in terms of the geometry as if they're distributed more widely. We'll revisit this slide a couple of times, but it's measured, it's quantified in terms of something called dilution of precision. And it's a constantly changing factor because of the fact that everything in the system is constantly moving, as is multipath and signal blockage, especially in urban areas with tall buildings. When the satellite signals reflect off those buildings before they arrive at the receiver, that distorts the actual time that was taken to get from the satellite. So whether it's a tree or a building or a bridge or a mountain, if they block the satellite or if they cause the signal to bounce around, that's not good. And of course, in the real world, it's a lot more complicated than that simple illustration. We have satellites that are visible, not visible, signals being reflected, signals being diffracted, and the quality of your GPS receiver and its ability to decipher these conditions come into play in terms of how accurate your location is going to be. I mean, there's consumer grade, mapping grade, survey grade. You can spend $100 on a GPS or you can spend $10,000 on a GPS, and you can be very happy with the results depending on what it is you're trying to accomplish. No matter what the situation though, you want to know your location with a certain degree of accuracy. And that uncertainty is what we're trying to minimize here. In this illustration, we're talking about one satellite, and that satellite itself has a range of uncertainty. We know we need at least 4 satellites to establish our location. So in the real world, we have overlapping ranges of uncertainty that end up creating an area on this illustration that's in red. That means we're somewhere in this area, but we're not exactly sure. We want to try and minimize this red area as much as possible. And one way to do that is something called differential correction. What if we had a base station where we had very accurately measured its location using survey techniques, and we put a GPS at that base station? So we know the real location, and then we read the value from the GPS. The difference between those two is an error. And if we are within maybe 150 miles of that base station and we take a GPS reading, that same range error, we can apply it to our reading and end up with a more accurate result. But I know what you're thinking, who has a GPS base station in their backyard? Well, I think another map now is in order. This is a map of all those base stations, constantly operating reference stations. NOAA maintains the map. And maybe this is a candidate for all maps are lies. Look at how some of these states really jump out. California, Texas, Missouri, Michigan, Indiana. The density of these in these states is much higher than the density in these other states. Now, whether that's really the case, I haven't looked into that, but I know in Missouri, these stations are maintained by the Department of Transportation to help with their work along the roadways. This system has been in place for many decades, and it works wonderfully well. There's a newer system that uses a satellite-based approach for this kind of differential correcting, and it's called a Wide Area Augmentation System, WAAS. This is North American centric. It has similar ground control stations that have been surveyed, so we know the accurate location. The offsets for a particular moment are transferred from those ground stations up to 3 geostationary satellites that maintain a position over North America. And then those satellites rebroadcast those correction factors back down to GPS receivers that are enabled to receive that WAS information. Currently, there are 3 of these satellites. There's a 4th that has been launched and will be expected to be online soon. You can go online and look at the status of the WAS system. This map kind of shows the extent of coverage, and as you get along the edges here, you get less accuracy. This system was developed by the Federal Aviation Administration, intended primarily for better automated approaches to airports in North America. So now that we know about some of the components and some of the ways that we can improve the quality of our signal, how can we use that to our advantage to give us better accuracy? Well, the first stop is this website, Trimble Planning Software. Trimble is a private company and a really big player in high-end GPS equipment. So this site gives you access to live information about the current status of every one of those GNSS systems that I talked about. This is a free site that you don't have to log in or have an account. You just go to gnssplanning.com. Along the left, you see the list of the satellites. And if you click through, you can get a lot more detail on individual satellites. But on the right is where you're going to put in the location where you're planning to go out and do some field work. So if I put in, let's say tomorrow, let's say we're planning to go out on Friday morning and start do some field work around here in southern Missouri. I've said that I want to see the conditions for 8 hours starting at 8 or 24 hours starting at 8 a.m. And I've said that I'll have a clear view of the sky in my location. So I get back a bunch of charts, including this one, which shows the number of satellites that will be visible as the day progresses. Starting on the left here at 8 o'clock, you can see that something happens here around 3 in the afternoon where the number of visible satellites drops noticeably. The green area here is the GPS system, the GLONASS system, Galileo, and the Chinese system. And you can see that they all have a drop in satellite coverage there around 3 o'clock. There's another chart or another graph that's generated that's based on this chart, which we've already seen about the geometry of the satellites, not just how many, but where are they located in the sky. The dilution of precision chart here shows around 3 o'clock. Sure enough, the precision gets worse there. So if I were going to go out and do a collection tomorrow in this part of the world, and I really was interested in high accuracy, I would not go at 3 o'clock. But we saw from that first chart that there really are way more than 4 satellites visible, especially if you have a system that can read across multiple systems. So you'd probably get some pretty good results tomorrow with a clear view of the sky. But what if I went back and changed this? What if I was doing a collection in an area where there was a tall building next to my site, or it was partially concealed under a bridge, or I was near a mountain, something that would limit my view of the sky considerably. And in this case, I put in 45 degrees as the limit to visibility. And you see now that even amongst the US system here in the morning, there are some times where I don't have 4 satellites visible. And as the day progresses, that's the case quite a bit. And if you look at the dilution of precision chart, these red areas mean you're not going to get any kind of a fix at those times, no GPS locations. So you probably want to do your collection in the afternoon for the best chance if you are dealing with that kind of limited sky view. Well, this is all really interesting, I think, to me. And if you're out trying to do a high accuracy GPS collection, but frankly, most of us don't plan our day around GPS satellites. We just want our phone to work. So let's take a peek at the whole GPS cell phone side of things and sort of compare and contrast with what we've seen to this point. All phones include a chip that's a navigation satellite system chip. It's a piece of hardware that is installed at the phone in the factory, and you can't change it. And that chip may read from multiple constellations, it may read from multiple frequencies, or it may not. But that hardware chip sets the limit on what your phone can do. And you can add apps that are going to take the output from that and do cool things like map your run, map your bike ride, but those apps can't overcome the hardware limits. Now, in 2011 in the United States, Apple announced that the iPhone 4S and all subsequent phones use not only the US system, but the Russian GLONASS system as well. And the iPhone 8 and later uses the Galileo system from the EU, and it uses Japan's system. And just a few months ago, Apple announced for the first time that way back with the iPhone 11, they started accessing the Chinese satellites, the Beidou satellites. So in similar timeframes, the Android world started using these other systems as well. And for many years now, the newer satellites have been launching that have the ability to broadcast in multiple signal bands. There's a band called L5 that gives a much better accuracy in many situations. And in 2018, the Broadcom company, which manufactures a lot of these GNSS processors, announced that they were making available a chip that would take advantage of these additional bands and allow cell phones to have, in ideal situations, perhaps 1 foot accuracy, which really is helpful in certain difficult geographies. So let's talk about 3 of the hidden location tricks that are happening right now in your little phone that's in your pocket: assisted GPS, Wi-Fi positioning, and barometers. So assisted GPS takes advantage of the fact that your phone is reaching out for assistance from a cell network to help with GPS. If you bought a brand new GPS device that's not connected to any networks of any kind, and you take it out of the box and turn it on, it's going to take 10 to 15 minutes for that device to make its first fix of a location. And that's because the signals that are coming from our satellites have been termed whispers from space. Part of that data that's coming to us from space is very detailed information about each satellite's orbit, its location, and that data set has to be downloaded into the device before the device even knows to start looking for satellites. Part of that data is called almanac data. It's more general in nature, and it is valid over a period of weeks. There's a more specific kind of information called ephemeris data that's only specific for a 4-hour block. And it's being broadcast from the satellites at a very slow baud rate. So what assisted GPS does is it gets that almanac and ephemeris data from the cell system, the cell phone network, which is much faster, and gets it into your phone more quickly and allows you to get a fix more quickly, a fix on your location. It's the difference between a cold start where you have to get everything in your device and a hot start. It's a much faster to a fix. So when you open your phone, you want to get a GPS fix very quickly, and this assisted GPS helps with that. Wi-Fi positioning. We talked about issues with GPS in urban canyons where you have multipath and block signal issues, limited line of sight to the satellites. That's what's happening in this illustration on the left. But your phone is always also on the lookout for Wi-Fi. And each Wi-Fi router has a unique ID. And there are companies out there like Skyhook and other companies that have built huge databases that equate a particular Wi-Fi ID with a geographic location. Skyhook's database has 5 billion Wi-Fi access points around the world linked to an XY coordinate for those Wi-Fi access points, as well as 200 million cell tower locations around the world. So your phone detects nearby Wi-Fi and uses that to pull a location from a cloud database that can enhance the GPS data that may be lacking in a particular location. And this kind of technology is also used indoors to help with indoor positioning. You may have visited a museum where you were given some sort of a handheld device, and as you walk around the museum, it gives you information about a particular piece of art as you're standing in front of it, because it knows your location based on this Wi-Fi positioning. I mentioned barometer. So why do our phones have a barometer measuring atmospheric pressure? Well, it's not for weather forecasting. It's to assist with location and specifically with elevation. Earlier, we talked about how the satellite geometry impacts the accuracy. We talked about how it's best to have satellites that are dispersed across the sky rather than having them all clumped together. We never really have the perfect satellite constellation though, because what we'd really like to have are some satellites below that are helping us to achieve a better geometry. And the Earth says no to that plan. So for this and other reasons that you're going to learn about when you take your first geographic information science class, this involves geoids and ellipsoids. The GPS elevation values are the least accurate of the values you're going to get out of a GPS receiver. The rule of thumb is that the vertical measurement is whatever the error is for your horizontal measurement, the vertical is going to be 3 times that. So you may be wondering right now what all this has to do with the barometer in your phone. Well, the answer is that short-term change in atmospheric pressure is a proxy for change in elevation. So the barometric pressure is not used to determine your elevation, but to augment it. So it uses, these apps use the GPS data to give you a baseline elevation. And then as you go out on your run or your ride, the elevation change is often detected based on the change in barometric pressure. So the GPS is used as a starting point. And you really shouldn't be relying too heavily on the elevation value that you get from a GPS device, other than to say, relative to my starting point, I've gained or lost this much elevation. Well, there's a lot going on in your phone. I think that's clear right now. How can you get a peek behind the curtain as to just what is happening behind the curtain of your phone? Well, GPS Test is an Android application that I recommend, and it gives you a very granular view of what's going on in your phone, individual satellites, which bands, which signals they're receiving. It's an open source product and there's no advertising associated with it. There's another app called GNSS Logger that has a corresponding desktop app called GNS Analysis that gives you access to very granular information if you're on Android devices. But if you're on Apple devices, Apple gives much fewer many fewer tools to access that kind of level of detail. There are apps like this that show you what's up in the sky above you at any given moment based on your location. It has cool augmented reality features, but it's not telling you what your phone is doing in terms of reading data from those individual satellites. To make use of this fantastic location data, there's all kinds of apps that you can do for running and hiking and cycling and whatever it is you're doing outdoors. Some of these apps use some wonky terms like tracks, which is a breadcrumb trail. Usually these apps, as soon as you turn them on, they start keeping a trail for you. Waypoints are locations that you explicitly store by clicking a button that says this is important and I want to store this location. You can give it a name and put some metadata in with it. And then routes allow you to string together those waypoints into a route that you might share with someone else. So once you get to be savvy with these apps, you can have a lot of fun with GPS. Here, we've attached a GPS to a common outdoor household tool. This work of art is called Mowing the Lawn by an artist named Jeremy Wood. You can check gpsdrawing.com to see a series of these over a period of years. When you look at the pattern there, you can start to ask some very serious questions about the efficiency of this particular pattern. Now, if you want to turn your workout into an art project, check out this site, gpsdoodles.com. Stephen Lund is the artist here. He considers Vancouver, Canada to be his canvas, his bicycle, his brush, and the GPS device gives him his paint. This giraffe, he covered 60 miles. This T-Rex, 25 miles of city streets there in Victoria. And my favorite of his works is this portrait of Queen Victoria, she's been GPSed. It took about 10 miles to make that happen. If you're looking to get your start in GPS art, here's the most simple GPS app I've ever seen. It's called GPS Sketch. It doesn't give you any readout about your latitude or your longitude or your elevation or your speed, and it doesn't have any maps. You just push a button and it draws a line as you move. That's all it does. It's a simple way to make your own GPS art. That's a very simple approach. The other extreme in complexity, I suspect some of the folks here who are Kansas City Chiefs fans saw this image of Coach Reed on NBC's Sunday Night Football 4 days ago during the Chiefs-Bronco game. Al Michaels called it crop art, but what he didn't say is it could never have been created without using GPS. It covers over 20 acres, and it was designed and built by a company called Precision Mazes from Lee's Summit, Missouri. They used this skid loader that's equipped with a very accurate GPS. You can see the antenna for the GPS that they've extended out there on the front. And then the operator inside the cab has a computer that he uses to trace over the lines that have been drawn by the artist and create this 20-acre image of Coach Reed. He was asked about it at a press conference this week, and he said he thought that they did a great job, but he wished that the artist had a better subject to work with. So that's fun with GPS. And this was created by tilling up the soil in an empty field. But next fall, when you're at a corn maze, this same technology is used to create corn mazes. So you're likely enjoying the fruits of GPS there. And speaking of fun with GPS, I'll close with this. I'm not sure if this really qualifies as GPS art, but my wife, Mary Jo, and I love driving trips. So I present to you here 20 years of Johnston road trips, all in the same car. And to give you a peek behind the curtain of how this map came to be, here's the dashboard of said car. Let's just say my wife, Mary Jo, is a very, very patient person. So there it is, the who, what, when, where, why, and how of GNSS. If you'd like to learn more, of course, there's plenty of resources. I think this book is a good example, Pinpoint How GPS is Changing Technology, Culture, and Our Minds. This is available in Linda Hall Library in their catalog. It's probably available in a library near you or in an independent bookstore near you. So a week from tonight, we'll wrap up our pursuit of mappiness with Mapping the Past. We're going to look and see how historic maps can help us see more clearly both currently and into the past and kind of link those two together. So we've covered a lot of ground here with GPS. I see Eric is back with us. I suspect there have been a few questions, and I'd be happy to hear some of those, Eric, if you could pass those along.
That sounds great. Yeah, it's interesting stuff. Do you know the frequency range for the U.S. system? It is apparently one that does not penetrate buildings, unlike, say, FM radio, right?
Yeah, that's right. All these systems broadcast in the microwave range of the electromagnetic spectrum. The ability to get a GPS signal indoors has improved greatly over time, in part because of improved signal quality from the newer satellites, but mainly because of improved receivers. I mentioned briefly the idea that newer receivers, especially that one from Broadcom, can do a better job of receiving the signals that are in different frequency ranges, and certain ranges like the L5 range can penetrate more deeply in through more solid objects. And so if a receiver is able to take both the L1 and the L5 and combine those and sift out some of the signals that are bouncing around through other buildings or through other materials, then it can do a better job. So really no GPS is going to be reliable indoors. There are other technologies that work better for that. So we probably will never have a time where the true GPS satellite-based system is giving our location when we're indoors, but there are certainly other approaches that are successful in giving us that information.
All right, Tom has a request that when you display a map, you tell us what kind of projection it is, and he has a smiley face there.
Yeah, that's somewhat. Tom must have watched last week's show. That's
I believe so.
I was noticing that WAS map and wondering if that might be a Peters projection, because it did look like the North America was kind of hung out on a line to dry like laundry. I'm not sure if it is Peters projection, but it might very well be.
Well, you've got me thinking about projection now. Every time I see a map, I go straight to that. Next question, why aren't the GPS satellites in geostationary orbit?
Yeah, that's a good question. So, you know, satellites that provide access to TV, like DirecTV or some of the others, those are geostationary satellites. So if you look up at the roof, every house that has one of those, they're all pointed in the same direction. Those satellites don't move. As far as the GPS satellites, I'm not 100% sure why the decision was made to make these movable, but I think it involves probably the number of satellites that would be required to give complete coverage. There's so much of the technical side of GPS that is well beyond my understanding, and the reason why they chose to use moving satellites instead of geostationary satellites falls directly into that category.
With all of the satellites up in space circling above us, and it seems like the number of satellites is increasing each year, do they pose any safety issues? I guess maybe as a follow-up, I could maybe a personal question add on to that. How well coordinated are the various GPS satellite systems?
Yeah, good questions both. If you Google space junk, you're going to find a very detailed map that shows the number of pieces of current and past space vehicles that are either intact or in pieces that are still floating around in our atmosphere. The GPS satellites at 11,000 miles and further from the Earth are in an area that's less occupied. The lower Earth orbit satellites is where most of that space junk is flying around. So I know that's something that's tracked very closely by the companies that are involved in this kind of business. What was the second part of the question?
Oh, how well coordinated were
yes.
the GPS projects? You know,
Yes.
did China work with the U.S. and Russia and the European Union?
Yeah, the book I recommended goes into some detail on that, and it's really quite an interesting political story. Of course, every country wants to design their system to optimize it for their own use, and that involves some overlap in some of these frequencies and some of the approaches that were initially proposed for the Galileo system, the Russian system, and the Chinese system would have created some issues for the US system. And believe it or not, through negotiations over time, all of those, most of those issues were resolved to the point where these systems can work together. I didn't really focus on that, but many of the newer GPS receivers take advantage of satellites from all of these systems if they're available. And it's to the point now where that the issue of having only 4 satellites visible is really becoming much, much less of an issue than it was when we were talking about only one system. Now the issue often is which of these 40 or 50 satellites that are visible are the best to be using. Which ones are most, you know, form the best geometry in the sky and are broadcasting a signal that I can use to greatest advantage. So the GPS world has changed drastically during our lifetimes, and there's no reason to think it won't continue to evolve going forward.
All right, Marcos would like to know, do the geomagnetic storms like we just had over the past couple of days, do they affect GPS signals?
Yeah, absolutely. The ionosphere that I mentioned is feeling the impact of those storms, and what that means is that those systems that are in place to calculate offsets and do differential correction for GPS, whether they're the core system that's land-based or the WAS system that's satellite-based, are needing to take into account how those satellite signals are impacted by changes in the ionosphere. So as those solar storms increase and decrease, the offsets for correcting GPS locations increase and decrease as well. And that's all handled by those augmentation systems that are intended to help with that very issue. So yes, the answer is definitely yes.
All right, the next question. If surveyed bases are used to improve the accuracy of GPS, how are the locations of those bases determined?
Yeah, that's a chicken and the egg question, isn't it? Well, those are surveyed using sort of traditional surveying techniques, which may involve some GPS, but old school surveyors had no GPS to use. And there are a network of control points that have been established by the U.S. Geological Survey around the country. And you'll often find those when you visit national parks or some significant overlook. If you look down at the ground, you may see a brass disc that's embedded there in the concrete. There are thousands of these around the country, and each one of those is sort of a starting point for surveyors who are looking to accurately locate, for instance, property boundaries. They go to one of the survey markers and start their process from there. It's really quite an interesting thing to try and track down the locations of those survey markers. There are so many around. There are groups who do that as a hobby and go out and find them. And they're so important, you know, to surveying, both they're sort of a relic of the past, but in the same way, they're the baseline for surveying today still. Now, surveyors, of course, use GPS, but they use it in conjunction with traditional surveying techniques that would allow them to locate a base station with extreme accuracy without using any kind of a satellite-based system.
We have a privacy question. Catherine would like to know, is there any place or any company that stores the data, received by GPS? You talked about using GPS on your phone to track, your road trip. Does Google know where you've been? And
yeah, the answer to that is a big yes. There are ways that you can turn off these devices. Your iPhone. It's interesting to me that the settings that allow you to turn off the GPS in your iPhone is under the heading of privacy. There's not you don't go to general GPS to look at this. You go to general privacy, and then you'll find the settings for location services. So you have the option of turning those off. And if you do, then all the apps that use location services are not going to work. The apps that you use to find restaurants, the apps that you use to find hotels, the apps that you use to track yourself when you're riding or cycling or hiking, none of those will work. So you certainly have the option to turn those all off. There's plenty of folks who are focused on this kind of thing, and there are instructions on how you can go out to Google and erase your history, your location history that Google has saved. Every time you add a new app to your phone and there's a bunch of legalese that pops up and you have to accept it. If you read through the details of that, often it's saying that we're going to be storing your locations. So folks who are concerned about privacy need to pay more attention to those kind of legal documents that you're agreeing to when you load apps on your phone. So yeah, privacy is a huge part of this. It gets more complex every day, and I think going forward, it may become even a bigger issue. You know, we talked a little bit last week about how most cartographers use these tools for good rather than evil. But there's certainly, you know, within the realm of possibility now that some of the things that George Orwell predicted in his work are coming to pass in our society today. So on the one hand, these things can be fun and we can look at pictures of football coaches etched into a field, but we also need to be aware that these tools can be used to limit our freedom, and it's a very serious thing to be concerned about. So I appreciate that question.
Cassandra writes, thanks from Massachusetts. Very interesting. And well, thank you, Cassandra, for tuning in tonight. We're a little past the hour. Let's do a couple of questions, couple more questions. SpaceX recently put up a large number of satellites. Was that for their own GPS or another GPS system? You know?
I don't know the answer to that. No. I don't know what the satellites that they're asking about were. I know that the most recent satellite that was launched in the US GPS system was launched the first week of November, came online the first week of December. I believe the next satellite for the US system is to be launched no earlier than July of next year. But I'm not sure what the SpaceX launch was about.
I don't believe it was GPS, but I can't remember either. So we'll end with this question, and it kind of ties into last week too, with people depending upon GPS. Are people losing their map reading skills? Do you have an opinion about that?
That's a great question.
Yeah.
There've been some research done on that topic. What comes to mind is the study that was done using London cab drivers and the analysis of their brains. There's a certain part of the brain that gets larger as you become more interested in geography and memorizing places and sort of having the ability to get from point A to point B from your memory. And the results of those research projects show that, yeah, as we use that part of our brain less, then that part of our brain shrinks. And the assumption is that means we're not as savvy to being able to use our innate abilities to get from point A to point B. So it's something that I think it's a gradual thing that's happening over time, but just think about how infrequently now you see a paper map. I think you can still pick those up at the interstate highway stops along the way, but you know, a lot of libraries have jettisoned their paper map collections or are thinning them out in ways that it's kind of scary, frankly, because just like books or other materials that are on paper, you know, it's easier to store them online or in digital form, but there's a certain, just like some people talk about how they like to feel the paper, they like to feel the permanence of it, and those of us who still have 8-track tapes or cassette tapes or old formats know that some of the digital approaches are great as long as there's a device around that can read those images or those formats. So yeah, it's something that, you know, we are not as good now, I think, as a people at being independent. We're becoming more reliant on these technologies in ways that may or may not be good.
That is true. And Jan writes, I like cassette tapes.
Yeah, that car that we did all those road trips in, it still has a cassette player.
Yeah, I love them too. And then Kent writes, SpaceX put up a bunch of satellites for their satellite-based internet system called Starlink. So.
Oh, okay, great.
Thank you, Kent.
Eric, I know we had over 500 people registered for this session tonight, and that's fabulous. I'm looking forward to next week, and we'll try and tie in some of the things we've talked about in these first two as we kind of look back and see how maps that may have been stored in dusty cabinets have been pulled out and scanned, and we can use those in combination with some of these new tools to give ourselves a window into the past.
Well, that has me intrigued already. So, and again, the third and final session will be next Thursday, December 17th, same time, 7 p.m. Central. Thank you, Kelly, for another just very informative program.